Hello everyone. So today I'm going to discuss in detail about modular multi-level converter based model predictive control. Model predictive control is a control which is uh, very advanced as compared to other control that exist in the literature. So today we are going to apply model predictive control on the latest topology of the converters, which is modular multi-level converter. I'll show you the Simulink implementation of this model predictive control, and in the end I will also compare it with the conventional PI or PID controller. So let's begin. So in this presentation, basically I am going to discuss about MMC topology and its operation, and why we are choosing the MPC for MMC. Also, I will briefly describe what are the limitations of conventional PI control. I will also discuss in detail about the control architecture that I have developed, which is a three-layer hierarchical control flow based on MPC. Uh, I'll discuss what is the current reference generator in MPC, and then we have a MPC phase controller. After current reference generator, there is an MPC phase controller. I will also discuss that what is the voltage balancing algorithm that you can use with the model predictive control, right? I'll show you the Simulink implementation of this, and after that I will show you the results that I got and how and why we say that the MPC is the best as compared to the other available conventional controls, right? So yes, we'll compare both the performance of the controls, and we'll conclude and discuss what are the future works available that you can follow. All right, so MPC or MMC topology and its operation. So the MMC is a modular multi-level converter which comprises of submodules. You can see here that there exist submodules, and these submodules consist of, you know if it is half bridge, it consists of two switches and a capacitor, and if it is full bridge, then it consists of four switches and a capacitor. So you can see there is a phase leg, complete single phase leg. So there are three phases, right? Each phase leg consists of arms, upper arm and the lower arm, right? And upper arm and the lower arm are connected together via an inductor. This inductor is necessary in order to limit the current uh, whenever the complete uh, arm is bypassed. So that current should be suppressed by using this inductor. It also suppresses some of the circulating current as well. So you need to carefully choose the size of this inductor, right? uh, Beside this, we have a DC terminal, we have a AC output terminal, right? And these are some key equations such as the arm voltage, phase voltage. The arm voltage will be equal to the sum of the capacitor voltages, whereas the converter voltage will be equal to the V lower minus V upper divided by 2. The AC current is equal to the IL is equal to I upper minus I lower divided by 2 approximately, and this is the circulating current. So the energy is balanced when EW energy of the upper arm is equal to the energy of the lower arm at its steady state, right? Next, yeah, this is very important to discuss that why we are choosing MPC model predictive control and what are the limitations of the conventional PI controller and what are the advantages of the model predictive control. All right, so when we talk about the conventional PI control, basically in conventional PI control, what we do, we have a decoupling and feed forward, which is required in the conventional, control. We have a PI control over there, which controls the, ID and IQ component for the, power control. Now, the limitations of this PI control are basically uh, such as slow dynamic response. Yes, the PI integrator introduces a lag. Yes, responses degrades during transients and reference steps. Right. So due to the integrator, we have a lag is there. After that, the PI control requires manual tuning. Yes, this is one of the you can say disadvantage of the PI controller, that it requires manual tuning. There are some auto tunes available as well, but tuning is very fragile as compared to the MPC. No direct constraints holding, such as current limits, arm energy constraints applied externally via clipping, and not symmetric, right? Separate balancing loop is there required. Capacitor voltage balancing required additional outer control loops, increasing complexity. Yeah, this is one of the limitation of the PI controller. Also, it depends on the phase lock loop. So if the PLL fails or there's a distortion from the grid, so it will directly impact on the control side or the control strategy, right? We also have a fixed switching frequency compared to the MPC. So these are several limitations that exist when you are dealing with the conventional control. All right. So why model predictive control? Why we should use model predictive control? Now, when we talk about the MPC, we have a direct constraint handling. So the current limits, your current is limited. You defined what is your maximum current, and energy constraints are embedded directly into the cost function. So no external limiters needed. So this is one of the advantage. Multi-objective optimization. Simultaneously optimize the current tracking, right? Switching frequency penalty and the capacitor balancing in a single cost function. So in a single cost function, you are basically your objectives are multiple, such as you track the current, you have a switching frequency penalty and you have a capacitor balancing in a single cost function, right? You have a lambda I, lambda SW, and lambda capacitor. So there are basically three lambdas are there, which is which are weights, right? No complex frequency domain analysis. Yeah, this is one of the advantage. Inherent nonlinearity, no linearization required. Handle the switched nonlinear MMC directly. Robust across full operating range. Yeah, this is one of the advantage that it is robust. Predictive anticipation uses system model to anticipate future states and eliminate phase lag inherent in PI integrators. So this is one of the advantage, that there was a lagging occurring. Lagging was occurring in case of the PI control, whereas this avoids the lagging. right? We have an integrated balancing capacitor switching mainly done by smart switching selection. No separate control layer required. All right. So these are the some of the advantages. There can be many other advantages, but these are the main advantages you can see that we got in the MPC. All right. So now we are going to discuss about the control architecture of the MPC. So here I have designed a three-layer hierarchical control of the MPC. We have a current reference generator. Then we have that current reference generator is basically gives us the reference current. Then for reference current for each phase, then those reference current goes to separate blocks for each phase, and there the magic is happening. I'm going to explain that in later in the next slide. All right. So here you can see that we have basically three different layers of hierarchical control. Now the first layer, what the first layer is doing, the first layer is taking the Pref, Qref, and VABC. Right, VABC is the grid voltage, right? And what it does, using the perk transformation, it is decomposing the ABC to DQ. Then there is a power current decomposition. Then there's a current limiter decided by the IMAX. Then it gives the IDIRF and IABC ref. ID and IQ are just for the measurement purpose, just for the uh, just to see that whether what the outputs are coming. Whereas the IABC ref will go into the separate phase in the layer 2. So in the layer 2 we have the MMC phase controller independently for each phase. Now what it takes as an input, it takes the current, it takes the voltage, it takes the upper arm current, it takes the lower arm current, and it takes the upper arm capacitor voltages, it takes the lower arm capacitor voltages, and it takes the IRF, which is the reference current given by the layer 1. And then it calculates via cost function, it gives us the modulating signal that is required to be given to the voltage balancing algorithm to generate a switching signal for each submodule, right? So NU opt and NL opt are basically the modulating signals that will go into the voltage balancing algorithm, right? So we have a three phase, so each phase will have these inputs, right? Then we have a voltage balancing algorithm. So what it does is select which specific submodules to insert based on the NU opt and NL opt and capacitor voltages via sorting algorithm, and it outputs, so it gives us the switching signals, right? So our MPC control will be in three layers. All right. Next, we are going to discuss about the current reference generator. So now, what it does, it decomposes P and Q references into the per phase current commands. So basically, let me show you. Okay, this is our MPC model. So this is the control block. Now here you can see that we have a active and reactive references given. We have IMAX given. All right. So basically, so this gives us these three reference currents. ID and IQ are just for the monitoring purpose. So if you can see, this is just a sinusoidal waveform. This is the current waveform which will go into the in each of the phase, right? So IL is the line current, right? VG is the grid voltage. Then you have upper arm current, lower arm current. So there are multiple inputs going in there. I'll explain them later, right? So these are the theory that applies in the current reference generator. You have a Fock transformation, you have a voltage decomposition, then you have a power current mapping, then you have a current magnitude limiting, inverse Fock, and power calculation. So this all is happening in the current reference generator, right? If you want to see in whole block diagram, so you have a Pref, Qref, then Fock transformation, then power decomposition, current limit check, inverse Fock, and then IABC ref. So this will go into the MMC phase calculator. Now we have a finite control set MPC for the prediction, cost function, and optimization, right? So our cost function in the MPC phase controller, our cost function is basically comprises of three lambdas. We have three lambdas, one for the reference current, one for the switching penalty, and one for the capacitor balancing. So lambda 1 is for the current tracking, and this is for the switching penalty, and this is for the capacitor voltage balancing, right? And what it does, so one step prediction model is there. We have the arm current, which is equal to the VU is equal to NU multiplied by VCU average, which is the upper arm capacitor voltages average voltage. So N is multiplied, and their arm voltage is developed, and phase voltage is developed, and predicted AC current is found via this Euler equation. And hard constant penalty, if the IL predicted is greater than the IMAX, then there is a penalty is applied. So the exhaustive search is done using the for loop, and the best cost is optimized and found. All right. So this is the overall block diagram of this. So you have the inputs IL, VG, IU, VCU, IRF, and NU previous, and NU uh, NL previous. Sorry. So these are the previous commands. We need to we should know that what are the previous states, and what will what is our current state, and what will be our the next state. So this is our MPC phase, right? So it predict IL based on the cost function, and select the best NU and based on the J. J is our cost, right? All right. So we have a capacitor voltage balancing based on the that the modulating signal we get. So let me show you. So here we are generating the current reference. Then we have a three different phase calculators, right? So they gives us NU optimum and NL optimum, and they all go into here, which is the modulating signal for the each method, or each your upper arm and lower arm. So for each upper arm and lower arm, we have basically three switching states, or the submodule voltage balancing states. We also need to give them a feedback, so that the controller tracks that what was the previous state, and what is our current state. This is necessary, right? So we have MU, A, MLA. These are the modulating signals of the upper arm and the lower arm. We have a capacitor voltages of the upper arm and the lower arm. Then we have arm currents of the upper arm and the lower arm. So these are needed in order to generate and develop a switching signals so that our submodule voltages should be balanced. So you can see there are three for each phase, right? So yeah, this is what is happening. Receive NU and NL opt VC, VCL, IU and IL. Then check if the IU is greater than 0. No. If this is no, then sort descending. Otherwise, if yes, then sort ascending. Charge low capacitor in case of this, and charge high capacitor in case of this. Select NU optimal submodules. Keep previous on if possible. Then fill the sorted rank and repeat for the lower arm as well. The same case is repeated for the lower arm. This was for the upper arm, right? So the algorithm rationale is basically explaining each and every step taking this. All right. So in the Simulink, I have let me show you the Simulink. So this is the Simulink model, right? We have a detailed modeling. We are using currently 4 submodules. So this is a universal bridge, and let me zoom in. So this universal bridge and a capacitor is connected across each bridge. We are measuring the voltage of the capacitor as well, right? And they are going into the control side, and as well as the measurement side as well. So this is the lower arm, same as the upper arm, and here we have capacitor voltages and the currents, the arm currents, IAU and IAL. So we are measuring the upper arm current and the lower arm current as well. So we need those in the uh, voltage balancing algorithm, right? Now this is the conventional control block. Let me show you. So this is the conventional model. Now the conventional model is uh, composed of PI controller, as I told you that yeah, we use PLL, and then we have a VD and VQ components, ID and IQ components, and using those we use decoupling and feed forward terms. So this is the PID controller, and this is the ID, and this is the ID ref. So reference minus mired goes into the PID. It gives you the the required D and Q components. You again convert them into the DQ to ABC using the DQ to ABC conversion. Then you generate the reference voltages. Then you have a PWM, and then you have a switching balancing voltage balancing algorithm for each submodule. So this is the conventional model, and this one is the MPC model. So that is the difference between both, right? All right. So let me show you the results. So the results tells us a different story. If I zoom in, so you can basically see this is the output voltage of the MPC. These are the capacitor voltages of the MPC. These are the grid voltages of the MPC. Now, if you compare them with the conventional control, so conventional control is different. This is the output voltages of the conventional control. You see there is a that effect, PWM effect is there. So yeah, right. These are the capacitor voltages. You can see there are a lot of ripples are there, but those were not present in the MPC based. So MPC in all terms is best compared to the PI control. Yeah, so the results are same results are here. We have the MPP MMC output voltage. These are the grid voltages. These are the submodule voltages of the MPC, and these are the submodule voltages of the the conventional control. So these are the output voltages of the conventional control. So if you compare a comprehensive, there's a comprehensive comparison between the MPC and the PI control, that the current tracking comparison. So there are the 4 to 8%, but with the MPC with the less than 2.1%. So this is better, 3 to 4 times better. Setting times we have 40 to 80 milliseconds, and this is the 25 milliseconds, twice faster. THD 5 to 8%, and in a case of MPC it is less than 4%. Capacitor voltage balancing 5 to 10%. This is plus minus 2%, right? Controller tuning effort, this is high, yes. Low, since we have a weights, more intuitive, right? Constraints handling external clipping only, and this is a direct in cost function, right? Fixed PWM in case of conventional, and we have a adjustable via lambda SW. PL selectivity is high, this is moderate. Computational load is very low, and this is computational load, right? Multi-objective optimization is not possible in case of conventional, and we have a native single cost. So yeah, in terms of THD at settling time and capacitor voltage balancing, MPC is significant and uh, better than the PI, right? So this is a conclusion that the hierarchical MPC framework was presented in this work. The control was shown, both the conventional and the MPC, and a three-layer hierarchical control was developed. DQ current reference used in the current, generating the current reference. Then we have the MPC based algorithm. Smart sorting balancing based on the MPC was presented. Less than 2% voltage imbalancing was obtained in the MPC, and it was shown that the MPC is superior, you know, less THD, 3 times faster dynamic response, 5 times better capacitor voltage balancing compared to the PI controller. So there are different, future works that can be, done. Extended prediction horizon, such as circulating current suppression, modular capacitor voltage balancing, grid fault right through, right, hill testing, and all that. So these are the references. Thank you very much for your time. Hope you like it.